Alright, in this video we're going to learn about measurement and calculation. And you can see these notes correspond to chapter 4. And this is Mr. Clancy. I'm looking forward to helping you understand about the importance of measurement and also what degree of uncertainty is allowed in measurement. These are some of the terms in terms of vocabulary that we're going to be going over. Some of them we've already touched on in class, as you know. One is going to be on sign notation, units, liters, grams, conversion factor, how we convert from one quantity to another way to express that same quantity, for example, gallons to liters and so forth. The Fahrenheit scale for temp density, we looked at that earlier this week with our golf ball density lab. The metric system, which most of the rest of the world uses besides the United States. The SI units, which are System International, you'll learn about those. MLs, mass. Equivalent statement is used in something called dimensional, do the conversions. The Celsius scale is the one that we usually use in labs. Specific gravity we'll touch on. The English kilogram, which is a unit for expressing mass. Significant figures, which we have started in class, and dimensional analysis on the Kelvin scale. The Kelvin scale is kind of largely used for gases. And we'll be talking about that in just a little bit. So let's look at some notes here, and then I'd like to work with you on a couple different. Now these notes, by the way, are going to be interactive. Meaning that I'm going to give you there'll be some problems along the way. I'll give you some sample problems that I'll work through with you, and then I'm going to give you, I'll leave some of them blank, you'll see as you go through. So it's a great chance not just to copy down notes, which is an important skill, but also to be able to translate what you're copying and in effect have really help facilitate your learning. So basically a measurement, let's start with a measurement in terms of introduction. A measurement always has two parts. The first part is a number, and the second is a unit. So that's important. We always want to get in the habit of writing it down. And however, the measure tells us something about the precision of an example that would go to 1/1000th of a gram. I could also have a scale that goes to just grams or tenths of a gram. The degree of precision is much different. What do qualitative and quantitative mean? Quantitative is an objective assessment. All right, if you remember the N for numerical. All right, she has hair that's 12 inches long. That would be an objective quantitative assessment, quantitative observation. Qualitative is more subjective. All right, the sky is blue would be a qualitative assessment, a qualitative objection or observation with that. So we'll just say not numbers related, if you will, necessarily. So objective would not change, basically. All right, if I make the observation or you do, whereas subjective could be much different. All right, now let's talk about sign notation. As we know, scientists use very large numbers or very small numbers at times. And we have to have a way to deal with those, all right? Just really helping deal with the zeros, making things a little bit easier. So it's important that you're able to use scientific notation. This monstrosity of a number you can see, this would be a lot of, press that in scientific notation, it would be 7.86 times 10 to the 11th, all right? Whereas if I have a very small number here, 0.0000786, that expressed in scientific notation would be 7.86 times 10 to the minus 5. So a couple of different sign notation expresses a number by doing the following. The main number, let's say the main number, which would be this main number right here. All right. Must be greater than or equal to 1 and less than 10. It cannot be 11 or 10 or 12 or anything like that. And the power of 10 is important on the exponent. All right. Large numbers, positive exponents. Small numbers, have negative exponents. And when I say small, typically I mean between 0 and 1. All right, have negative exponents. It's not a negative number necessarily, but it is a negative exponent. All right, so if I move the decimal place to the left, all right, it is a positive power of 10. All right, therefore 15,000 becomes 1.5 times 10 to the 4th power. All right, I went over 4. Here's my decimal point. I went over 4 places. All right, if I move the decimal point to the right, the number is going to be a negative power of 10. Therefore, 0.00015 becomes 1.5 times 10 to the negative 4th power. Again, this is a positive number, but the negative 4 indicates a small number, not necessarily a negative number. All right. Let's go on to page 2 of our notes here. And you can see I've got a number line with that. And just some examples to show you. All right, where does this negative second fall in the number line? Well, I'm going to say it's someplace in here. Okay, it's probably a little bit less than that actually, but it's very big there with it. Next question is 1.6 times 10 than 1.6 times 10 to the minus 4? And the answer is it is bigger. All right. One of them would be 0.016. This would be 10. 1.6 times 10 to the minus 2 versus, let's see, we're going to have 0.016. All right, this would be 1.6 times 10 to the minus 4 because I moved that decimal point over that many times. All right, let's go ahead and try a few here. And then you've got a few examples to work on your own, which we will check in class. All right. So this number here, 0.00001, would be equivalent to 1 times 10 to the minus 5. All right. That'd be 1 times 10 to the minus 4. 0.001 would be 1/1000th, or 1 times 10 to the minus 3. The next one, 0.01 would be 1/100th, which would be 1 times 10 to the minus 2. 0.1 is 1/10th, as you know. That would be 1 times 10 to the minus 1. And 1.0 is 1. You might remember this, the 10 to the 0 power. This would be 1 times 10 to the 0 power. All right? So, what I'd like you to do is to work on these. You can stop the video now as you do that, then pick it up later. What I'd like you to do is to work on those by yourselves as you go through that. Now on section 5.2 of our text, I want to look at some of the SI units and give you some tips on how measurement is actually done. All right, we'll also look at some of the symbols for that. So the units of measurement for science are called SI units, from the French organization, if you will, called Système International. This is like a large organization. These chemists and scientists get together once a year, stay in a nice hotel, have some nice meetings, but basically they get a few things done, and they decide to say what's the common measurement that we're all going to use to measure length and time and volume, because it's important that scientists collaborate. Why don't you make a note of that? Scientists have to collaborate. It is very important. You might be doing a lab and you want to share your results with someone in Sweden. You've got to have a common way of measuring it. So let's look at these units. The system, the unit for length is meter. And that would be again, very important. Time would be second, all right, which is just a little s as an abbreviation. Volume would be liters, and that's usually represented by uppercase L, also very important. Mass is actually kilograms, which would be kg. All right, temperature would be kelvins. I mentioned earlier this is the one that's often used, not exclusively, but often used in the gas law. This would be K. Also, Kelvin says no degrees, like we have degrees Fahrenheit, degrees Celsius. We'll come back and I'll explain how that works later on. And pressure is Pascal. Pascals. Or PA. Big P, little a. Now, an important equivalence relationship is that 1 m at 1 cubic centimeter. We're going to see this in our lab when we do a measurement challenge lab next week. And for water, 1 cc, which is a cubic centimeter. Cubic centimeter. All right. And a cubic centimeter, just think of a cube. And the dimensions of the cube, 1 centimeter on each side. That's what a cubic centimeter is. All right, so 1 cc, this is used, the cc, by the way, is often used in medicines and stuff. 1 cc is equal to 1 cubic centimeter, cm3, which equals 1 gram for water. All right, why does this work for water, not for oil? Because oil is less dense than water. All right, so those are important things to remember. All right, let's go over prefixes for this. Prefixes for the units of measurement. All right, let's go over all these, and I'm going to explain to you which are the single most important ones you have to know. All right, mega would be 1 million. So if you say someone has megabucks, if you talk about how much money they have, that would be $1 million. Kilo. Notice mega is uppercase M as an abbreviation. Kilo is 1,000. All right, deca would be 10. So if I had a deca grams, deci would be 1/10. All right, so this would be 1/10. Okay, centi is 1/100th. We know there are 100 cents in a dollar, correct? All right, milli is 1/1000th. .001, or 1 times 10 to the minus 3. Micro is 1 millionth. See if I can squeeze that in here. 1 millionth, which would be point, I'll just say 10 to the minus 6. All right, and nano would be 10 to the minus 9th. I think I could squeeze that in here. 1 over 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hope you can all see that. That's a fraction for that. The ones that you absolutely, positively, unequivocally have to know, I'm going to circle. These are also bolded on your notes. You must know kilo. You must. You must know centi, 1/100th. You must. You must know milli. No doubt about it. You must. All right? So, we need to make sure we've got those three down. All right? And then using the SI unit for grams, 1 kilogram would be 1,000 grams. So I'm using this prefix along with the SI units that we looked at over here. All right? A centigram would be 1/100th. A milligram, which we'll work with in this lab, will also be in the lab this year, I should say. A milligram is 1/1000th of a gram. All right? All right. I want to finish 5.3 for the first video here, and then we're going to initiate the rest of the notes on a different video. Let's look at measurement of length, volume, and mass. These are critically important. You'll get a lot of experience doing that this year. The SI, or System International Unit for length, is the meter. All right. How many centimeters are in 1 meter? Well, there are 100 centimeters in 1 meter. What is the equivalence statement between 1 inch and centimeters? So this is an English to metric conversion. This is a good number to remember. 1 inch equals 2.54 centimeters. We're going to look at this later when we do some dimensional analysis. How many meters are in 1 kilometer? There are 1,000. Let's just give you a little bit of practice. What's the equivalence statement between mile and kilometers? In other words, how many miles does a kilometer equal, or vice versa? 1 mile equals 1.61 kilometers. Maybe some of you have done a 10K race, which would be, I have, which is 6.2 miles. All right. These are equivalence statements. I want you to become familiar with this term. These are equivalence statements. They help us to understand one unit in terms of another unit. And you can see they can be used, they can be turned into conversion factors. We'll talk about that later. The SI unit for volume is the liter. All right, this is the three-dimensional space. You got to think about how high, depth, length, and width of something has.